Here we have a capacitor that is connected to a source and a resistive circuit. For t less than 0, the switch is closed and the capacitor is connected to the source, and so the capacitor will have built up some charge, will have some voltage across it. Once the switch is opened at t equals 0, the source will be isolated from the capacitor, the source will be doing its own thing, and so the capacitor will discharge across the resistor, the remaining circuit connected to it. So if we want to find the voltage V across the capacitor, the first thing we need to do is look for t less than 0 and find what the voltage across the capacitor is before the switch is thrown, so the starting voltage. So we'll start by drawing the circuit as it is before t equals 0, so the switch is closed. Before the switch is opened, the switch has been closed for a long time, and so the system must be in steady state, and so we'll draw the capacitor as an open circuit. So here we have the circuit before the switch is thrown. The switch there is closed. The switch has been closed for a long time, so the capacitor is acting like an open circuit, and V0 is the starting voltage across the capacitor, and that's what's going to drive the behavior of the capacitor once it starts discharging. So we need to know what this voltage is across this capacitor. And so what we need to do is look in the rest of the circuit. We see that the capacitor is in parallel with the resistor, so whatever voltage we have across this 550 kilo ohm resistor is going to be the same voltage that we have across the capacitor. So let's try to find the voltage across this 50 ohm resistor, or 50 kilo ohm resistor. Well, these two are in series already. If I can do a source transformation and turn this into a voltage source and a series resistor, all of my resistors will be in series, and I'll be able to do a voltage divider to find the voltage here, which will be the same voltage there. And now I can do a voltage divider to find the voltage across the 50 kilo ohm resistor, which will be the same as the voltage across the capacitor in parallel. And so we see that the 50 kilo ohms represents 1/3 of the overall resistance, and so the voltage across it will be 1/3 of the overall voltage from the source. And so the voltage here will be the voltage across our capacitor. That is going to be our starting voltage, and we'll need that to come up with the equation for the voltage across our capacitor. Now that we've seen the behavior of the circuit while the switch is closed, now we'll look for t greater than 0 after the switch is thrown. We're going to redraw the circuit with the circuit that's connected to the capacitor after that switch has been opened. Now we have the circuit for t greater than 0 after the switch has been opened. We need to use this circuit to find the time constant and recall the equation for that. The capacitance is given, and there's only one resistor connected to it, so we can find a number for tau. We found tau, so we can write that over here with the rest of our values. Now that we know the initial value of the capacitor voltage and we know the time constant, we can plug into the equation for capacitor voltage. Once we have the capacitor voltage, we can find whatever else we're being asked. So we go back to the problem. We're asked for the initial value of Vt. That was the 200 volts. Whatever the voltage was before the switch was thrown, that's the same voltage we have after the switch is thrown, because the capacitor voltage is continuous. We were asked for the time constant, and we've found that as well. We're asked for the numerical expression for V of t. We found that as well. The implication here, because we derived this for t greater than or equal to 0, this is valid for t greater than or equal to 0. We're asked for the initial energy stored in the capacitor. There is an equation for that. We know the value of the capacitor. If we want the initial value of the energy, that would correspond to the initial voltage, which we have as well, so we can plug in and calculate that. And so we found the initial energy in this case will be 8 millijoules of energy stored in that capacitor. If we want to find the amount of time it takes to dissipate 75% of that energy, we need an equation for the energy as a function of time, and we have one of those as well. This is the energy that's been dissipated as a function of time. We want to know when we've dissipated 75% of the original energy. So the original energy was this amount here. That's what we found originally, and we're looking for when we have 75% or 0.05 of that value. And so we can plug in the numbers there, but we don't really need to. This part of the equation and that part of the equation are going to cancel. Here, if we want to know the time at which this happens, we only need to solve for t. And so we can find the time at which that takes place, about 14 milliseconds.